Right, so I wanted to tie up some of the things we've been talking about in the last few lectures and talking about many body systems in particular. So just to remind us where we are. So what we have is thought space. So we have some n identical particles. It could be bosons or fermions. And there's some single particle Hilbert space that describes each one of those particles. And we could restrict ourselves to a finite dimensional Hilbert space, or we can think about this as an infinite dimensional Hilbert space. And for all states that we're calling phi in this single particle Hilbert space, we assign a set of creation operators and their adjoints, the annihilation operators. And they have the property that all the creation operators commute with themselves for all different states, or anti-commute if they're fermions. And the commutator or anti-commutator of the creation annihilation operator is given by the inner product between those two states. So this is a basis independent formulation for Fock space. And if these states were, if I had a collection of basis states, then I can assign creation annihilation operators to each of the basis states if these are orthonormal states. Then we have the relationships that we're familiar with for this set. Okay, so what we were discussing at the end of last lecture, was if we think about this Hilbert space being the one associated with, say, particles in infinite dimensions, or, I'm sorry, particle moving in space, where the Hilbert space is infinite dimensional, and generally we would take that Hilbert space to be the square normalizable functions over whatever space we're talking about, say in three-dimensional space, and then the spin degree of freedom, right? Where D is whatever the spin is, whether it's a fermion or a boson, depending on whether this is a half integer or integer spin. And so that Hilbert space, a particular basis we could choose for that might be position, and then whatever the spin is, that's a perfectly good basis. Well, it's good in the sense that it's a way we can write representations in that space. So if, or we might have momentum space. And for this particular basis, there's a very special set. So often we're interested in, say, three particles, in which case we have some, the individual states of interest are often momentum eigenstates. So quite often we're thinking about, say, the creation operator associated with a given momentum and a given spin, and you know, let's just give this, as we said, some label sigma, which label sigma is the nth s value. So the creation operator with that, we typically would write just as a function of p. It's a continuous function of p labeled by whatever spin value we have. And the creation operator that creates a particle at a particular position in that spin state, we typically call the field operator sigma, psi of x. And in particular, thus, we see that these guys satisfy for either bosons or fermions if we look at those as this is Kronecker delta, and this is where these are Dirac delta functions. Because this is nothing more, of course, by the general rules that we wrote down, the inner product of those basis states and that inner product is the Dirac delta for the continuous variable and the Kronecker delta for the discrete eigenvalue, right? Okay, so let's take this a little bit further. Let's think about this a little bit more. As we said, we can always do change of bases. For example, what we discussed previously is if I had, for example, the creation operator, if I have, say, two bases, say EI is the basis for this space and FI is a different basis, then for the Hilbert space H. And these could be discrete or continuous bases. We'd have to think about that appropriately. Then the creation operator, say, associated with, let's call this, or as we did previously, and let's say B, the creation operator associated with a different basis. Then, as we discussed, I could look at either the creation or annihilation operators associated, transfer from one basis to another. The BI's are related to the AI's by the same change of basis matrix that I would have by those bases. Okay? So we could, as we discussed, say go from the creation operators or annihilation operators associated with position to the creation annihilation operators associated with momentum. And there we have to do a change of basis through, instead of a sum, an integral. Right? That's just this rule, where now the change of basis is from P to X, where here it was from the F's to the B's. All right?
Shouldn't be the daggers?
No, this is correct. Okay. The other relation is this. The way you always remember it is these are like bras and these are like cats. Okay? So, if this is like a bra, and a J, then that's what this is. Yeah. That's how you remember it. All right, so with that said, this is correct. And this is pi. Well, that's nothing more than the position representation of momentum eigenstates, which are plane waves, right? So this is equal to the plane waves e to the I k dot, or p over h bar dot x. And then my annihilation operator for that. Yes, Stephen, you had a question.
No, I was asking, I was going to ask why B dash goes to A dash, but then I realized what you were doing.
Okay. So this is the representation of the field operator at position x in terms of the creation operator, in this case annihilation operators, for momentum p. And this is a form we see all the time. I can do other kinds of things. For example, suppose I have the creation or annihilation operator, doesn't really matter, for some state phi in my Hilbert space. Okay, this could be a wave packet. Okay, let's look at the creation operator. What the heck? Okay, so this is the creation operator that creates a particle in the state, which I can think about in the wave packet phi. I don't have to think about creating it at a position or in a momentum. I can think about it creating it in any wave packet I like. Okay? And when applied to the vacuum, this creates a single particle state. It's not an eigenstate of positional momentum, perhaps, but it's still one particle. Right? Now, how would I write this as a superposition of creation operators that create them in position x? Well, according to this rule, that's equal to this. And I could give it, if you want, there's a label also sigma associated with it. If I want to let it have spin, which I generally would. And what's this?
Is this a Gaussian?
Well, whatever it is, it's the wave packet, right? It could be a Gaussian, but it's just the wave function. So this is how you would write things that, create a particle in that wave packet. Okay. Or, if you like, I could write it in momentum. And then this would be the momentum space wave function. So I would weight the creation operator associated with each momentum component by the momentum wave function, and that, again, just another way of writing the same thing. All right, what about operators? As we discussed, if I have an operator which acts on a single body and it's symmetrized over all the bodies because it's an identical particle system, then we can conveniently write such an operator on the Fock space, right? So if I had a one-body operator, O, which that acts on the single body Hilbert space little h, then of course this is just a matrix representation of it, but then I have to symmetrize it over all particles. And once I do that, I promote it to the Fock space. Okay? So on the Fock space, this operator has this form, right? It annihilates a particle in I and creates it in J. Okay. Now, what about if I wanted to instead, suppose this is an operator on my symbolic Hilbert space, but on my Hilbert space, explicitly, as it generally would want to, includes position degrees of freedom, right? Yeah.
Any reason why you switch order bases there? We went from IJ to JI.
No, this is Ji. So this is the number,
Yeah.
OIJ. And then I made a mistake. Thank you. Thanks. Right. So this should be indeed IJ. Thanks. Yep. All right, so now let's suppose I have this operator that is an operator that acts on the motional degrees of freedom of the particle. Okay? So, suppose I wanted to write the position operator on the many bodies space. Okay? So position operator. So this in the single body Hilbert space is diagonal in the position basis, right? That's the position operator. In the, this should be rounding brackets because this is on the single body Hilbert space. Okay, so I'm using round brackets for checks and bras and little h. Or if I wanted to, I could also write this in momentum, in which case this is not diagonal, it's h bar over minus I, the gradient with respect to p of the delta function. That's what we did some many moons ago. That's the momentum representation of the position operator. It's the derivative in momentum space, right? Again, rounding brackets. Or, if I look at the momentum operator, well, of course, that's the gradient with respect to position, and then I just won't leave, I'll leave that off because that's the obvious gradient operator. It's the off diagonal there, but it's diagonal in the momentum representation with I being values p. All right? So now I ask you, how do I promote this to the Fock space? Any suggestions? So how do you generally promote this to the Fock space? We have this general rule over here, which tells me, well, wherever I saw a ket, I have a creation operator, or I have a bra, I have an annihilation operator, right? Associated with that particular state. So what's the position operator now on the main body space?
Just replace those with the A dagger.
Right, and in this case, A dagger and A are psi, right? That's the thing that creates a particle at position X is the field operator psi in the non-relativistic many-body theory. I make this caveat about in the non-relativistic because it actually is very subtle about the notion of localizing at a position if you have a relativistic theory. You can localize it in momentum, but you can't localize it in position, it turns out. There is no position for say, the photon. That's another story for another day. But we're non-relativistic, so let's be non-relativistic. And but what we have in that case then is the position operator would look like this. That's kind of interesting. I mean, and what about the momentum operator? Well, I'm not sorry, no, in momentum representation, I plug this guy, it becomes A of P, right? I mean, generally I would have to have also spin. Let's just, for the moment, let's just look at the spin zero case. These are bosons, but it's not a big deal. I would just put a label on them. I just don't want to, I don't want to emphasize that point at the moment. Well, if I plug that in, this becomes, you know, the creation at P, now it's P, and then I do integration by parts, get rid of the, move the delta function, then this becomes integral over P, A of P, the gradient H bar over I, minus I, the gradient with respect to P of that. And the momentum operator looks like notice the form of this. If you were doing wave mechanics, and I asked you, had a wave function, psi, what is this? Well, if I took halves off of this, what would this be?
Wave equation.
It's not the wave equation. It's got wave functions in it. But what is it? If suppose these were wave functions rather than the operators, these are not hats.
G.
If I asked you, what is this? Psi star psi. What is that? It's the expectation value. This is the expectation value of momentum. This would be psi squared. This would be the probability density to be in P, right? These look like expectation values, but they're not. In the second quantized version, they're the operators which, when we take the expectation value, would have exactly the form we would expect from the expectation value. Okay? But they look like that. Ew.
You should have class next semester, like in the afternoon, so it has time to dry.
Right? Okay, so that's kind of cool. What about the number operator? Well, the number operator is equal to, in some sense, is the second quantized version of the resolution of the identity. Let's see why that's true. So if I know that in with respect to the single body Hilbert space, this is the resolution of the identity, right? So that's the identity. But if I second quantize this, Well, this becomes an A dagger, this becomes an A. This becomes N. And so it counts the number of particles, total number of particles, because I have more than one. This is N sub I. The number in that ith state. How would I write this in terms of the field operators? What is the number operator written in terms of my field operators for position and momentum? Well, there's lots of ways to go about that. I could just change the basis the way we just did and relate creation and annihilation operators there and then use them to weakness. Or I could just say, well, a resolution of the identity with respect to position is this, right? So this becomes an integral over all space of psi dagger psi. Again, if these were wave functions, this would be 1 if this was normalized. But this is now the number operator. Or, equivalently, in momentum space, this is A dagger A. Right? So, how do I interpret this?
It's like counting all the particles over all space.
It is, right. So it's the total number. It's the total number in the system. So what about this operator? What is this operator? So if these were not operators, but wave functions, how would you interpret what this is? Besides our psi, which would be the probability density, the probability to find a particle in that region space. But now this is the particle density operator. This is where the term density operator kind of comes from, I think. So this operator is the particle density. Operator. Not to be confused with density operator, which means something, right? So this operator, say the expectation value of this would be the average, the expected number of particles I would find in a region d cubed x around x. And similarly, this operator is the momentum density operator, right? Note, remember that in continuous variables, these operators have units, unlike the ones that were labeled by cats in Hilbert space. If they're labeled by these improper cats, position and momentum, then they have units. The units related to this 1 over the square root of whatever we're talking about. What about this operator? Where x is not equal to x prime. Well, this operator is kind of the second quantized version of this. Okay. Well, that's interesting, because if I looked at in the first quantized version, once again, so this is my hint. This is the operator that's on little h. If I were to look at the expected value of that in single particle Hilbert space in first quantized language, what is that? Well, the expected value of this is the trace of the density operator with that, right? Which is the off-diagonal coherence in position. It's the elements of the density matrix in position space, and it has to do with coherence. Remember, the off-diagonal elements of the density matrix tell me something about the ability to see interference between those two alternatives. So this operator, if I were to look at, say, the expected value, is saying something about coherence at two different points in space. Yeah?
This density operator, you mean the partial density operator, right?
No, in here, this is the density operator that we learned about last semester.
Oh, so it's not the same in.
It's not.
Okay, okay.
All right. Okay. So if we generally want to solve, let's look at sort of a generic type of many-body problem we might want, that one often encounters. So very typically, the Hamiltonian for the system would involve some kind of Hamiltonian that acts on the single bodies. And then typical are, the interactions are pairwise interactions, overall pairs. Okay, that's a typical kind of many-body thing we would have. Yeah?
Just a really broad question.
Uh-huh.
You know, you could in principle do this all in first quantized form, right?
Of course.
And so, why,
Yeah.
like, is it because it's a lot easier to represent these things?
Yeah, so, you know, what we had been discussing over the last number of lectures, we started with first quantization. But first quantization is generally an awkward formalism for the following reason. We have identical particles. So the way we deal with that is that we give all the particles labels, and then we symmetrize or asymmetrize over them. And so in some sense, we throwing the labels away. So we add in these artificial labels, particle 1 and particle 2, but they don't have any meaning, and it becomes a very awkward, especially when you have more than just two particles. Then it really, for two, it doesn't really make a difference. So the second quantized formalism becomes particularly important when you're dealing with many body systems. Although, you know, I think if you're looking, you know, so you a lot of typical, say, you know, quantum chemistry kind of analysis is often done in a first quantized form. So it can be done, it's just generally more awkward. Okay, so this is my typical form, and I'm assuming that these pairwise interactions are symmetric. In other words, it doesn't matter which two. The form of the Hamiltonian of this is the same. That we've seen examples like this. For example, if I thought about an atom with lots of electrons, right? Then what are these Hamiltonians? Well, the single body Hamiltonian would be the following. I have the kinetic energy of some electron, the ith electron, and its attraction to the nucleus, right? So that's, and then I have, you know, that, all of them. And then this would represent the Coulomb interaction that is repulsive between the two electrons. And it's a symmetric form. It doesn't matter, split I and J, it's symmetric under that exchange. Okay? So this is the typical kind of system, and it's almost, as I say, it's fairly generic. I mean, this was for electrons interacting with one another, but we could think about bosonic atoms that collide in a trap and interact through their hardcore interactions and would, you know, lead to some kind of many-body collective material, okay? So this kind of Hamiltonian has generally the following form. If I wrote it, say, in second quantized notation, there's lots of ways to do it. Let's do it in the position representation. So now I'm going to write this in second quantized form. Well, what would this be? Well, the single body operators, we know how to write. We just had examples of them. So they'll look like expectation values. So we have something that looks like that. That's my single body Hamiltonian. And then I would have something we know, we recall from our studies, we have to symmetrize this, so we have the 2x and x prime, e squared x minus x prime, and then 2 creation operators. And 2 annihilation operators. Now, these I really should, because these are electrons, I really got to take into account my spin states, because these are fermions. So I have, this is a one-body effect, and this is a two-body effect. The bodies here are electrons, okay? And they can be either spin up or spin down as my choice of writing these field operators, okay? Now, this is generally, as we said, a problem that can't be solved. I mean, people make their living solving this equation for, you know, especially if you have molecules, not just an atom, you have multiple sites, and you want to solve for the Born-Oppenheimer orbitals. So there are different approaches to dealing with them. One is what's called mean field.
Yeah, I have a quick question.
Yes.
In a two-body term,
Yep.
it's normally ordered. Did you know?
Yeah.
There's something that I know about that.
You do.
That should-
If you had been at the other
Okay.
lectures, then you would see that that's how if it's the same kind of problem that we had. If I have a two-body operator, in first quantized language, it would look like that, summed over all those. These become my annihilation operators, these become my creation operators. So this has the right form on the, this is how you promote a two-body operator. It's automatically normally ordered. All right, so now what do I mean by mean field? So this is a complicated problem because, well, you know, what I have is a bunch of electrons, right? I mean, maybe this is uranium I want to solve for the ground state of uranium. There's a lot of electrons there. And they're all, there's a lot of potential correlations I have to take into account for. But the mean field approximation is basically say the force of repulsion that this electron sees is due to the average effect of all the other electrons on average. And that's a very typical way that to lowest approximation, we take that into account. Now, the way that that's done, you might just say, well, I'm going to replace wherever I saw some density of particles, just replace it by its mean value. Okay? So this would be a way of getting at this problem. Say, well, I'm going to turn this into a one-body problem by saying some particular electron, what it really sees is just, we'll turn this into an average. And then it only sees what the other electron is doing on average. But the way in which that's done should properly account for the fact that there are quantum statistics, which means the local density electrons see depends on their spin states. Because if two electrons are in the same spin state, they can't be at the same place because of the Pauli exclusion principle. So the way that that's typically done is by a method that's known as Hartree-Fock.
Is it the same Fock?
It's the same Fock, a Fock space, a different Hartree. Yeah.
But by the way, so the expectation value is with respect to what state?
Well, that's exactly the question. If you knew, then you have the answer. What the solution is to try to find the self-consistent mean field solution. And that's what Hartree-Fock does. So Hartree-Fock says is of the form of a variational principle that we talked about at the end of our lectures. And the variational principle says you make an ansatz. You make an educated guess. And then you minimize the energy. And the solution is definitely not lower than the absolute ground state. So the true ground state energy is always lower than that. Yeah?
Another question. So here you circled the coherence term, right? And it's actually the density because...
Yeah, it's actually the density. It's actually the density. So I'll come to that in more detail. So what the Hartree-Fock approach does is to say, let us make an ansatz that captures this mean field spirit. And then just minimize the energy. And then you have a self-consistent solution that has a mean field. So what is the Hartree-Fock? What the Hartree-Fock approximation basically says is to assume that I can write as my ansatz a single state where each electron is in some orbital that I don't know what that orbital is. That is to say, it's described by a single Slater determinant. What do I mean by that? Well, so what I'm saying is, let's suppose I have, n electrons. So I'm just going to say that I'm going to fill them up with fermionics. So I have, say, let's just say I did this for So this guy has 5 electrons, okay? So I make an ansatz. I say I'm going to fill up these orbitals. There's orbital 1, fill it up and down. Then there's orbital 2, fill it up and down. There's orbital 3. Doesn't matter, put it up or down, doesn't matter. Each one of these is associated with some orbital. Phi 1 of x, phi 2 of x, and phi 3 of x. I don't know what those phi's are. My job is to find what those orbitals are that minimizes the energy. This is the Hartree-Fock ansatz. It's in some sense a separable ansatz. It's just sort of a product of wave functions. They're not really products because it's symmetrized, but relative to the Fock space is what we would call this a separable state. It doesn't involve what we would call strongly correlated electrons. It's a mean field, saying each electron is kind of its own thing and it sees what everything else is doing on average, but it's not correlated in any way that I'm going to be taking into account. This is a kind of uncorrelated ansatz. So you plug this in to, so this is my ansatz, or the state. And I then take the expectation value of that. That's going to be the sum of all the single particle energies. And then it's going to involve terms, as we discussed last lecture, or not last lecture, the last lecture where we talked about helium, that involves both the direct interaction and the exchange interaction. And we minimize that. And what you end up with is a set of equations that look like this. For every one of those orbitals, I'm going to have a Schrödinger equation that looks like this. I have the single particle Schrödinger equation that represents the attractions of the nucleus. And then I'm going to have the following kind of equation. So this is for whatever spin that is. Sum over sigma prime. E squared r minus r prime sum over j okay, so this term represents one. I'm not done yet, but this is one of the terms. This term represents the Coulomb repulsion seen by this electron due to all the other orbitals on average. So it's a kind of shielding effect that shields the attractive force that one electron feels the nucleus due to the average over all the other.
So that's d cubed r prime.
Yeah.
Yes,
Okay.
indeed. D cubed r prime.
That could be taken out.
Yeah, thank you. And then, but of course I have the exchange term, which has the opposite sign, right? So this is what we call K, and this is what we call J in some lecture, which involves, for all these not equal to the orbital of interest, because they're the same orbital, then this is 0. D cubed r prime. So that's the exchange term. So this is a set of coupled, nonlinear PDEs, and this is equals the energy of the ith orbital. So this is sort of the binding energy of that orbital. So this is a Schrodinger-like equation. If I didn't have this, this would just be, you know, each electron unaffected by all the others attracted to the nucleus, and this would be the Schrodinger equation that we would know for each orbital. But this is the mean field equation, which gives us a way of trying to self-consistently solve for orbitals under the assumption that I can just think about them as uncorrelated, where they're, whatever that orbital is and that energy is, this is a hard set of equations to solve. But this is what one would do to try to get at the structure of any body system. Let's look at an example for bosons. Okay, so let's suppose I have the same generic form, but let's suppose I have the following problem. It's a problem that's very much in vogue. So let's suppose I have n bosons in a trap. Okay? So I have some kind of atom trap. And I can just fill it up with my bosonic atoms. They're rubidium-77 atoms. Okay, they're bosons. And I wanted to describe the dynamics of that many body system. Well, the Hamiltonian is something we can write down pretty easily. Let's just say they're spinless bosons, so that actually they're spin 1 if they're rubidium, but it doesn't really matter. I can fix one of the magnetic sublevels and just say I'm looking at that one M state, so I'm not even going to label it. Okay? So what's the Hamiltonian? Well, the Hamiltonian in this case would be the single particle Hamiltonian and interaction, so collision. That's how the bosons interact, they collide with one another. Okay? So from a single body perspective, in the first quantized language, I would have kinetic energy and the potential energy. Right? That's just for a single particle in a trap. Right? This is the potential energy of the trap. And the collisions, well, let's just say that they were contact interactions. The particles have to be right on top of one another. Right? So this would be equal to the potential, the collision potential, would be some constant, I'll call it A naught times a delta function. So with whatever the right is, this has to be the energy. Okay. So what does this look like in second quantized form? Well, again, we would have something that looks like that's the single body term. And what about this? What would it look like? Well, it would have that same form that we wrote down over there, except now it's a delta function. This would be they just have one because it's a delta function. It would look like that. Right? Because the x prime is equal to x in that problem. Again, this is a hard problem to generally solve. But I can look for the ground state of this system. Now, if these were non-interacting particles, what would be the ground state of this system of bosons?
I'll just collapse it.
They would all be in the ground state of the single body Hamiltonian. They would all be in the ground state of the simple harmonic oscillator. They would pile up, right? That's what we call a Bose-Einstein condensate. All particles. Now, what would be the mean field ansatz, the Hartree-Fock ansatz here for bosons? In contrast to this state. So in this state, I filled them up because of the Pauli exclusion principle. I've had first orbital up, down, then second orbital up, down. So what would be an ansatz, a Hartree-Fock ansatz? Here.
All remains the same.
Exactly, all in the same state, but I don't know what that state is. This is the Hartree-Fock ansatz. Well, actually, this, right? So all bosons in the same orbital, but I don't know what that orbital is. If there were no interactions, you know what that orbital is. It would be this orbital. But now, due to the interactions, well, they're going to be in some slightly different orbital. And when you minimize that equation, you get the following. So the minimization of the expected value of the Hamiltonian leads me to what's known as, would look like the following. Minus h bar squared over 2n L squared plus v of x sine of x plus a n minus 1 So my orbital that defines the state where all of them are in the same orbital satisfies a kind of nonlinear Schrodinger equation, right? Which depends on the number of particles, which gives it a certain energy. And this is a kind of problem that people study all the time. It's a form of what's known as the Gross-Pedievsky equation. It's not exactly that, but it something like that. Equation. So that's a way we can solve for the dynamics of a Bose-Einstein condensate. All right. So, what about dynamics in the problem? So here I just said, let's look for the ground state, mean field. What about dynamics in the problem? Well, that's generally a hard problem. There's one thing I just want to show you, which I think is an elegant result from second quantization. Let me go to 11 because there's a
Left 30.
I mean, whatever the next 11 is. Really true?
Yeah, left 30.
Oh, yeah, okay. Oh, yeah, it is. It is, I forgot that they didn't change that clock forever. I'm confused. Yeah, okay. We said 11:45, but we may go to
You used 11:15.
Oh, did I? Oh, that was interesting. All right. Let's talk about dynamics because I think it's a very nice result. Well, so we have, generally speaking, the time evolution operator. If it's a time independent Hamiltonian, we know that's the time evolution operator, right? Now suppose my Hamiltonian was a single body Hamiltonian. So there were no interactions between the particles. Every particle just undergoes its own evolution. Okay? And I'll call this is the Hamiltonian. Now that Hilbert's. Okay, let's suppose that's true. So I have H that's my single body Hamiltonian. I'm not saying this is not necessarily in the basis of energy eigenstates. It's just it's got some matrix, right? And my single body unitary in the first quantization would look like that, right? And it was H's and H bars. And if I wanted to know what the state was as evolved as a function of time, I would just apply this. To the state. Now, how does this work in Fock space? So suppose I have, so this, in Fock space, this is equal to that, right? So now, suppose I want to know how a certain state evolves. So let's suppose I have, at time t equals 0, the state is one particle in the state phi. So how does this evolve as a function of time? Well, I apply the time evolution operator to this. Right? And I can shove in a u dagger u. Right? And what is this?
Vacuum.
That's the identity, right? It goes right to the vacuum because u doesn't do anything to it, right? Because every time it gets hit by an annihilation operator, it's 0, either the 0 or 1. So that's this. So what I need to calculate is this. Right? Well, what is that? Well, this, I can write this if I want as sum over k look at each basis state having expressed phi in terms of the basis. Okay, how am I going to calculate this? Any ideas? This is my unitary.
Can you use the Baker-Campbell-Hausdorff?
Thank you, sir. Use the Baker-Campbell-Hausdorff. Right? So this, remember, e to the a times b, e to the minus a is b plus a b plus a with b over 2 plus etc. Right? Okay, so let's do that. So in this case, this whole thing is A, and this is B, right? So I need to consider the commutator, whether these are bosons or fermions, what we showed last time, it doesn't make a difference. We showed that this commutator was equal to Ki delta Jk. And so I do it over and over and over again. And what do I get? So this will be equal to AK plus, or I should say minus I sum over I J H sum over I and J H I J H K. And then I do it again and I get the same K square. I'm gonna have to keep track of all those factors somehow. So at the end of the day, what do I get? At the end of the day, what I get is that this evolved operator is nothing more than the time evolved. This is just, again, the exponential. I guess I should have the time here. Exponential of the Hamiltonian over h bar t on the state ak, which is to say ak dagger. So here's the bottom line of this. This detailed calculation is ultimately goes to the following. This thing is equal to this. In other words, the time evolved creation operator is just what you would expect. It just evolves that state. So if I had, another way of saying this is that you guys should recognize this. What the time evolution operator does in the case where there's no interaction between the particles, where each particle just evolves individually, it's just equivalent to saying you mix together the bases according to the single body unitaries. And it's a trivial solution. So if I have a photon coming into an interferometer with all kinds of beam splitters and stuff in it, well, that photon gets transformed into one photon in some other superposition of momentum states, and that's what this is stating. All right, let me conclude with one other thing. So we've discussed this in the context of bosons and fermions. But in some sense, the formalism of second quantization is more general. In the sense that if I have a Hilbert space that is either completely symmetric or completely antisymmetric under exchange of particles, well then, I don't care whether they were bosons or fermions, they're just they're described by that Hilbert space. So where's a context where that might come up? So let's consider n spin 1/2 particles, or n two-level systems. They could be, I could think about them because they're isomorphic to spin 1/2 particles. Okay, let's say I have n of those. Okay, now if they're, let's just say that they're distinguishable. So they never overlap in space. They're at completely separate positions in space. And when they don't overlap in space, as we discussed, I can ignore anything else. Whether they're, the notion whether they're fermions, in this case they're actually, if they're actual spin 1/2, then they're fermions, but they could be two levels of an atom. And I don't care whether that's atoms, is a fermion or a boson. I do not care because they don't overlap in space. So if I were to ask you, what is the Hilbert space associated with that system? What would it be? Yeah, it's a tensor product of, and also I have two-level system, two-level system, two-level system, two-level system. It's a complex of two, right? And this is the dimension 2 again. Okay? Now, there is a special subspace of this Hilbert space. Now, remember, if I think about these as spin 1/2 particles, I can think about those subspaces in terms of the total angular momentum. So this Hilbert space, of course, decomposes into Hilbert spaces that have a definite total angular momentum. That total angular momentum ranges from a possibility of 0 to a possibility of n times 1/2, the maximum possible j. And there's some degeneracy factor, but I'll just write it loosely like this. Okay. Now, what can I say about this space? So let's consider the space. Consider the subspace. With j is equal to n over 2. Okay. Let's consider that subspace. Here's an example of a state in that space. J is n over 2, m sub j is n over 2. Okay? How do I make that state out of my spin 1/2 particles? Well, they all are spin up, right? So this is the state up, or tensor, tensor, all the way, all of them up, right? That is the state, that state, the only state that has m sub j, they must therefore have that j, okay? What about the state where j is n over 2 and m sub j is n over 2 minus 1? How would I obtain that state? I'd obtain that state by applying the lowering operator, right? So this is, proportional to the lowering operator on this state. Doesn't change j, but it changes m. Now, I can get that lowering operator is just the sum of the lowering operators on each spin, right? So this is equal to the sum I equals 1 to n, the lowering operator sigma minus on the ith spin. Okay. So let's do that. What do you get? Well, you're going to get, it lowers the first one. And then the second term lowers the second one. Dot, 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 dot. So each term in this, it's a superposition where one of the spins was lowered. but I don't know which one. And then I would do it again. And then I would get 2 lowered, but I don't know which 2. So every state in this space, notice, is symmetric with respect to exchange of any 2 spins. This state is obviously symmetric with respect to exchange of any 2 spins. And that would be true for the next one. And how many different such states are there? Like the orthogonal ones. N plus 1, right? Because I start. How can I see that? Well, one way to see it is the dimension of the space is 2j plus 1, right? 2 times n over 2, n plus 1. Where n plus 1 those states. Those states are sometimes known as the Dickey states. Now, okay, this is where I want to conclude. This is interesting because this says that this space, symmetric subspace of V spin is isomorphic to a set of bosons, right? So this space is isomorphic. So this subspace is one and the same as a set of bosons. To n bosons in 2 possible single particle states. Obviously, these aren't bosons necessarily. They could be bosons. They could be 2 levels of bosonic atoms. But so this space is isomorphic to the following space. I have some number spin up, some number spin down, where the total n up plus n down is n. And these are bosonic. These states are a dagger to the n, a dagger to the n minus, n down, over the square root n factorial up, n factorial down, acting on the vacuum. So it's a 2-mode boson. A boson that could either be in state up or state down. Okay. Again, this is, they're not actually bosons, but I could just write them as bosons.
Notice that you mentioned n plus 1 enters in this isomorphism.
Count it. Remember, we did that counting.
Okay.
We have to say, how many different ways can you put n particles in 2 boxes? And the answer is n plus 1. So, this might be looking familiar if you did your homework at some point, where we talked about the Schwinger representation. Remember that? So, let's conclude then by just seeing how this in fact gives us the Schwinger representation. So, for example, if I have single body operator, well, the only single body operators here are the Pauli operators, right? So I have sigma x, which in, say, the standard basis is, and I can think, say, j over 2. So jx is this. Jy is sigma y 2. And sigma from Jz is sigma z over 2. Let me call these little j's. These are my single body operators. I want to promote this to the many-body space in the subspace that is symmetric, the space that has a total, right? So this is like sigma plus, sigma minus, right? So this is J. How do I promote this to the many-body space? Well, we just saw how to do that. The bras and cats get replaced by creation annihilation operators. So I can write it as in a kind of bastardized notation where this is, with respect to the standard basis, let's write them out. Jx is a half a dagger of minus plus a dagger of a y. That's where the Schringer representation is coming from. So I always remember it, because I know what sigma plus and sigma minus are. It's just the second quantized version of the Pauli algebra. And it allows us, as we saw, to deal with arbitrary spin states we were able to describe. Well, there's a lot more to say, but I think I will conclude there. I think you probably now have a foundation that you need to go on. You start thinking about learning about many-body physics. The one thing we're always going to talk about is the connection between fermions and spin 1/2, the whole Jordan-Wigner, but I'll put some things up there. Anyway, have a great